Okay. All right. Welcome to part 2 of the tutorial. For those of you who are here and chose this over the sunset, I appreciate that. So what we did was in part 1, we had a very, very quick tour through the foundations of this, and in part 2 now we come to so this was basically all other people's work, and we now make a jump towards an old work of other people. We make a jump towards the 21st century and talk about mostly work in my group, actually. But first, a little bit more background as well on computational models. So what we're going to do now is we're going to exchange one of those things by a box, and inside of the box is now something more technical, where it's set before perceive and act. We now have ASR, which stands for automatic speech recognition. On the perception side and on the acting side, it's NLG, that stands for natural language generation. So we're assuming that speech goes in and speech goes out. And in the middle is a component called DM for dialogue manager. So I will be talking about the dialogue manager in such a system for a bit before I move on to other things. Okay, so here's yet another way of putting this. We have our agent. An agent has a sensor and an actuator, and something is happening on the way from the sensor to the actuator. So this is the typical AI picture of an agent, I guess. If we want to formalize this a little bit, we call the sensor readings, the measurements, we call them YU, and we call the things we do in the physical world is also a sequence we are labeling Y prime M. We have a special kind of situation here, namely we are in an interaction with another agent. So we're not just acting in the physical world, but we're also acting vis-a-vis another agent. And we're making the assumption that the other agent is following intentions. The other agent is doing what they are doing because they intend to something. They intend to be doing what they're doing, and they may be doing it for because they have another intention. The idea is that we cannot perceive these intentions. We can only perceive physical events, and we have to infer from those physical events via our sensor readings. We have to infer what these intentions are. So what we have is an A with a little tilde on top, which is the approximation of the intention of the other agent. Okay? And the U stands for user, because we normally talk about users of dialogue systems, of those systems that can use language. And the decision component in the middle in this line of research is called the dialogue manager. We're also making the assumption that the dialogue manager has a state that it's in, and that based on our approximation of the user intention, we are updating the state. We're transitioning from one state to the next. Okay, and if we want to formalize this, the job of a dialogue manager is to compute this update function. Based on the current state we are in and our approximation of the user's intention, of the user intention, we compute an update of our own state. And based on the state, now updated state we are in, we compute the best action to take. Okay? There are various ways of doing this, sort of roughly sorted here in order of flexibility, let's say, or complexity. And I will very briefly go through 3 of them, very briefly, just sort of to give you a taste of what's going on. So the simplest one, the first one I'm going to talk about is FSA, finite state automaton-based approaches to computing this update. And the idea, well, for computer scientists, this is very obvious. The idea is that really inside this function really is specified as the transition function of a finite state automaton. And the transitions are triggered by the input, by computations of the input. So we start our dialogue maybe by saying, hello, how may I help you? And then the user says, I want to travel to Berlin. And then the system asks them from where they want to travel. And then they say something. And then the system guesses that this is what they meant and then computes a reply. So this is a typical travel agent dialogue system. Of course, you will have spotted the problem immediately. What happens if they don't say what you expect them to say? One of the alternatives you expect them to say, well, then you're going to have a problem. And the problem is nicely glossed over here as else, and else brings you an eternal loop. So if you say, hello, this is the travel system, how may I help you? And then the person says, yeah, I want to visit my granddaughter, and this is else. And then the system asks, from where do you want to go? And then you say, well, she recently moved to somewhere. And then the system will get completely confused because that's not in the plan here. That's not in the finite state automaton. But funnily enough, well, if you've ever used a customer service dialogue system, this will not surprise you. This is the way commercial systems mostly function. There's a finite state automaton in there. Obviously much more complex than this, but most of the alternatives will be handcrafted, and someone will have thought this through. One of the reasons actually is because the customers of the companies that produce these systems, they actually prefer this. They want to sign off on any of the utterance that the system is going to make, because they are potentially held liable for what the system says. So they really want the most control they can have over what the system will produce, meaning that a lot of it is actually handwritten. If you've used Apple Siri, it will be also clear to you that many of the replies are handcrafted, and they are little one-off patterns of utterance and reply to it. Oh yeah, that's true, right? Yes. So in call centers, they're actually following a script as well. And very annoyingly, they may even be calling a script when they call you up. So they're not allowed to deviate from this. Right. So this has the advantage that the search space is small. That helps ASR. That helps decision making. But it has the disadvantage that dialogue doesn't normally work like this. It isn't normally that well pre-specified. In the first part, I talked a little bit about the phases we have. Sort of the greeting phase typically is more or less codified, and the exit phase of a conversation is more or less codified. But what happens in between isn't so much. And even if it looks like, if you're having problems, then for humans it's quite possible to deviate from the typical path and to flexibly react to these problems. If it's not in the FSA, in a dialogue system, then you're out of luck. You just have to hope that they have a counter in the else loop, and if you're in your fifth iteration of this loop, they will jump back to the beginning, or they will jump to a person, right? And it's actually sort of a dirty secret of research on speech that if you do this in many of these systems, if you make them fail often enough, you will get a human. And most people who work in this area, they will immediately do this. They also don't want to talk to these systems. Okay. Well, annoyingly, I can say that annoyingly, ASR isn't so much a problem anymore, thanks to these improvements through deep learning and other things. ASR has gotten quite well. So it used to be the case that we, as people researching dialogue management, shifted most of the problems. We said, oh, well, the ASR is just so bad. The input is so bad. That's not quite the case anymore. But still, thinking through a conversation like this is quite difficult. Okay, so sort of at the other end of the complexity spectrum is an approach that is actually from the high time of the BI approach from the 90s. James Allen and Perot, I forgot the first name. Ray, yeah, Raywood, yeah, Perot, they applied the ideas that were around at this time of modeling the mental state separated into beliefs, desires, and intentions, of using this approach to model communication as well. That's very tempting. I mean, in the first part, this is what I had as the mental state for the agents as well. And you may argue that you need more than this. You may need obligations as well as a construct, not just beliefs, desires, and attention, also social obligation. But it is clear that this is a theoretically very pleasing analysis. Unfortunately, it does get a little bit involved. So if you have something like, can you give me a list of flights to Berlin? Which on the surface looks like a yes-no question, right? Clearly that's not a yes-no question, but it looks like one. And the nice thing is that the BDI approach can explain how you go from this looking like a yes-no question to a request to be informed of something and to a desire on the side of the system to give a reply. But this is a fairly long chain of inferences. And as you know, this tends to be a little bit brittle. And it falls over, even though it looks like it should be quite flexible, because it is deriving this from first principle, it turns out to be actually very brittle, and it just falls over if things happen that weren't expected from these in these inference rules. I'm not going to go through all of this, but we go from something that looks on the surface like a request to be informed if you can do something, and then you need a principle that tells you that often if someone wants to know if you can do something, they want you to actually do the thing that they're asking you whether you can do it. And you go from the other person, from believing that the other person wants to know if you can do this to believing that the other person wants to be given this, and from that you go to intending to actually give it and to give the reply. And then you would answer, and then you would plan, you would do some planning. If I'm in the state where I as the system want to give some information, then I perform an inform action and I actually give it, right? Yeah, so historically this turned out to be actually in the end a lot less flexible than you would have hoped for, because these rules were very difficult to maintain, and it was very difficult to judge the consequences that your whole system of rules will have. And then you ended up with systems that failed to do something like this, or they would just say yes to a slightly differently phrased indirect request. So that was a line of research that wasn't really followed so much. It's coming back, interestingly, a little bit. In the same way, I believe it's coming back in AI more in general, because there are better ways now of modeling beliefs, desires, and intentions probabilistically in systems that don't fail that easily. I'll mention one of those here. So an approach that, at least in academia, has had more impact recently, instead of using a conversational scoreboard, which basically is the mental state is structured into various elements. Something like plans of the system appear here as well. Beliefs appear as well. Split typically in something that is assumed to be private to one agent and things that are assumed to be shared. But the way you get from, oops, was this all? No. The way you get from one state, from one structured state of the dialogue to another is via these update rules. And the update rules, they're sort of sitting in the middle between inference rules and simple transition rules in a finite state. automaton. Again, I'm not going to go through this in great detail, but the point here is it's not quite modeled from first principles. It's not quite modeled on the level of if someone asks a question, they typically want to know an answer. If I know the answer, then I should give it. But rather it's modeled in terms of protocols that just write this down, these connections between move types. The advantage here is that you factor out a little bit, you specify treatment of clarification requests, for example. You can specify this separately from the way your dialogue is supposed to move forward on the task level. That's an advantage over the finite state automaton approach. So in this particular example here, we have noticed that a parameter is missing to confirm to this request. As I said, the point here is that this is a nice balance between leaving some things to inference rules and fully specifying other things. A more recent approach is to use Markov decision processes, especially partially observable Markov decision processes, where you're modeling the transition from one state to the next. First of all, you're not making the assumption anymore that you actually know with certainty in which state the dialogue is in, but rather you model explicitly your uncertainty as a distribution over states, right? So with a certain probability, we are in a state where we have established that the user wants to go to Berlin, but we are also leaving some probability mass for the fact that we may be mistaken and they actually want to go elsewhere, right? And we train this via reinforcement learning, so we choose actions based on this distribution over states, and during training time we receive a reward for this, and in this way we learn the best, an optimal action function under uncertainty. This, on the other hand, has the problem that the state space can just become huge very quickly, and it becomes very difficult to represent, even just represent the state space, and also to explore it during training because it's just too big. So you end up partitioning the belief space, the state space, and you end up with something it's not as impressive anymore than what you may think, because you had to cut it down quite a lot. Okay, but this is I think mostly what I wanted to say about dialogue. The various approaches of writing dialogue managers. The general point in any case is based on an approximation of the intention of the other agent. Decide on how you want to update your state, and based on that, decide on how you want to act. Okay, so that's one aspect. How do I make the decision? And most existing systems, if we move to the temporal level now, most existing systems, they actually make an assumption that is fairly odd, and I hope it is odd for you as well after the first part, after the way I've set it up. So what they do is, typical implemented dialogue systems, what they do is the user is speaking, and the only thing that's active while the user is speaking is the ASR, is the speech recognition, right? And only when the speech recognition has recognized silence of a certain length, only then will it endpoint, will it end its work. It will maybe do another pass through the audio, and will then pass on the text of the utterance to the next components, and they will then do their thing, and then they will produce a reply. And this is typically something like 750 milliseconds, so the silence has to be quite long, so it's not mistaken with the silence, for example, that we do when we produce plosives. You need a little silence before you do this. sounds like this, right? And you don't want to fire too quickly, so it has to be probably even higher than this. Does anyone see what the problem could be with this? If the system is not even starting to think unless it has perceived some silence, yeah?
If it's your little old grandmother telling you life history, she may never stop.
Yes. Okay. So this is one way of saying, I guess, is you may want to produce a reaction while the person is speaking. So silence is actually not a very good, and it goes both ways. It's not a very good marker of the end of an utterance, because well, humans typically are able to find the end of an utterance way before. They don't need silence. We've established this in the first part. And also there may be other reasons for silence within an utterance. I can be thinking, I can have started to say something. Yesterday I saw the brother of, right, so you can be silent within your utterance. And in a system like this, it would have mercilessly endpointed, it would have tried to understand the partial utterances, it would have passed it on to the other modules, and they wouldn't have known what to do with it, right? So for various reasons, this is not a very good idea. And this is one of the reasons that conversations with these kinds of spoken dialogue systems tend to be very robotic and unpleasant, right? Because there's silence. After you've said something, there's a long silence, and you don't really know what the silence means. It doesn't actually mean anything. It just means the system's processing. So that's one limitation, and the other limitation is that most of these systems, they kind of treat the situation as one where only the voice gets through, right? So they're typically telephony systems where the only information channel is voice. And in our research, we want to overcome both of these limitations. So what we do is we work on situated dialogue, where the minimal criterion for something to be situated dialogue is that we take seriously the fact that the participants in a dialogue share the same timeline, share a common timeline. So when A is acting, this action is immediately perceived by B, not just after a silence or so, but the action is immediately perceived, and B immediately has the chance of reacting, and if B doesn't react, then that's a reaction as well that needs to be understood, right? So we have worked on systems that are purely telephony as well, but we are taking more seriously the fact that they are actually in the situation together, and they have shared responsibility for the time. And being silent is actually the silence, typically the silence of someone. Someone is being silent. It's not just that no one is speaking, but someone may be supposed to be speaking and is not, and that's meaningful as well. But also, in a more narrow sense of situated dialogue, we have looked at situations where the participants are actually co-located, which means that they can see each other, they have a visual contact, and they see third things in the world as well. And they can assume that there's some common knowledge about these third things in the world, in their shared physical environment. Okay. I'll talk a little bit about incremental processing and turn-taking. That's something we've done a lot of work on, but I will talk more in the light of the interests of this network about our recent work on grounded semantics. We have come up with a sort of a variation on this information state update model, which we call the IU model, the incremental units model, which is meant to model the fundamental skill of an agent to form hypotheses about the world. And our IU model is, and that's the sort of distinguishing feature, it's a temporally fine-grained model of the information state of an agent. So that's what it adds over the literature. Okay. Because common concurrent system, what they do is, as I've said before, when an utterance comes in, they wait a bit, and then they make one update. So it's a bit unfortunate that it's so low down on the slide. So this is a little notation we've devised. This This diamond here means this is the moment when the update was made of the information state, and this is the content of the update. And the red line is the moment that we are looking at the system, which happens to be the moment at which the update was made. But the utterance actually was made sort of in the past. The utterance is already over at the moment when this update is made. Right? So this is what typical systems do. And we started with the assumption that we want the information state to be updated more often with minimal units of information as soon as they can be hypothesized. Do you have an idea what a good minimal unit would be if it is speech as input? If the unit is not the whole utterance, but you want to be smaller than that, you want to be faster, there's a very natural unit that utterances come in. Smaller, a thing smaller than, okay, I'm avoiding to say sentence here because we make a distinction between utterances and sentences, but sentences have a smaller unit inside of them, yes? Okay, you're already too low down. You could be, but I was going for words here, just right. So there's a very natural way we segment longer linguistic actions into smaller actions, namely the performance of words, the utterance of words. You could go further down as well. You could divide the words into sequences of phonemes or syllables and then phonemes. But I was just going for the words. And this is actually what we do. So we changed our speech recognizer to give us output incrementally after each word, roughly. So here we would get an update that take was set, and then a little bit in the future we get the update that take the red cross. Okay. When we started doing this almost 10 years ago now, this was sort of newish. These days it's not so spectacular anymore, which is good, which I'm happy to see. But systems like I think Google started with it. They work incrementally now as well. So if you speak into Google now, you will get an output word by word rather than waiting for the full utterance. Siri only did this with a recent update, but also Siri is now working incrementally. And I'm happy to say that at least in the Google ASR, there is something that is a much better developed version of something that we published a couple of years ago. So yeah, so people even in the commercial world have seen the usefulness potentially of this.
Now I need to ask, how you define a word acoustically? Just what your definition is. How do you segment the utterance?
Right. So this is something the ASR gives us, and the way it works on the ASR level is you have a dictionary, and then you have HMMs that tell you phoneme sequences. Wow, that will sound nice on the recording. Okay. You have HMM, hidden Markov models, that tell you this, but you're making a good point here, which will occur, I think, on the next soon. I will come back to this problem. Yes, it's not obvious where the word boundaries are in spoken speech because you blur words together, right? Okay, so this was the first assumption. The second assumption is that higher level hypotheses can be formed on the basis of lower level ones. So in our system, we're not interested in, per se, in the sequence of words. We're interested in the meaning. So what we do is we immediately try to process this. We get a word in, and then we compute its semantics. And this is here the level of semantics, where semantics is using the same word, but using a different font. So that's the level of semantics here. So take is modeled by take in a different font. Okay, so take the red cross, and you would obviously after this update, but you would try to develop your semantic representation in lockstep with the word recognitions. And these brown lines here mean that this is grounded in that. That I'm assuming that the semantics is this at that point is because I have recognized the word here, right? And this may look familiar now because, again, this is a hierarchy of understanding. It mirrors this ladder, this action ladder on the analysis side, right? So you're not just attending to the behavior, you're not just understanding the signal, you're also trying to get at a meaning of it. Okay, so that's all very nice. Unfortunately, if you do this incrementally, you add a new dimension of uncertainty. I mean, this is already rife with uncertainties. The ASR could be wrong, and your semantic construction could be wrong. But here we also have the added uncertainty that we don't know what the future may bring. And in the light of new information, we may have to revise old information. So here's an example that I think makes this understandable. Let's say some audio came in and our ASR says, yep, I know that, that's the word for. Great. Unfortunately, more audio comes in and now the ASR is saying, ooh, sorry mate, that wasn't actually for, it was 40, right? So I have to take back my hypothesis that the word that we're dealing with here is the word for. It is actually the word 40. Okay. So this is an honest to God mistake. There's nothing that the system could have done. For really more or less is a component in 40. And if you are going down on a lower level, on a phoneme level, you wouldn't have to revise anything. But the way you package these phonemes into higher level units, you have to revise. You have to say, okay, this really isn't 40, this is 4, here the word. Right? But now remember that our little model, in our model, we've already started processing based on this hypothesis, right? I have a slightly different example here. Let's say take the red. So the first hypothesis was red, but then the ASR says, oh, it wasn't actually red, it was the word right. Right? And if we have already built some semantics on the assumption that the word red was said, that the word right was said, sorry, and then we have to take back this higher level hypothesis as well, right? So we need to do a little bit more bookkeeping. That's the main point here. This is not just an academic sort of problem. ASR can be very unstable, right? If you want to be very incremental, if you want to be very fast, then you have to live with a lot of revisions, a lot of taking back hypotheses. So you have to find a good operating point where you're not overwhelmed by revisions, but you're also quite fast. We have several papers trying to define the problem there and trying to find a good spot there. But this depends on the behavior of your ASR. Okay. So this slide is meant to point out that this notation already is quite rich. We can read a lot of this notation. So we have the moment when our snapshot of the information state is taken. We have the moment when the update was made. So this is a system event, but it's drawn on the same timeline here as the real world events, right? So we have the real world sound event, and at some point we make an update in our system, and this update is actually talking about moments in time in the real world. So this assumption here is that this stretch of signal is actually the word take. If you can read these spectrograms, these representations, then you will notice that this is not actually the word take. The word take would look completely different, but this is a waveform I had lying around. Anyways, so yeah, the important point is we have these links that link the levels of processing, and we have links in green, which you can't really see, that link hypotheses on the same level. And this is a way you can encode lattices, for example. You can encode alternatives. What else? And also, so this would be a more fully specified system where you have ASR, a part of speech tagger that tells you which types of words these are, and then syntax and contextualization and the dialog manager. We can also model in this model decisions of the system that concern the future, right? So this here would be the dialog manager has made a decision to produce a certain act, and this action manager then has planned an action to happen in the future, and so on here up onto the level of speaking. There are interesting parallels between planning and interpretation. There's uncertainty about the future in a similar but not the same way as there is uncertainty about the past, right? Because the future just may not pan out as you have planned it, right? You may not be able to actually say what you plan to say, but you can still make plans about it. And just, I'm sorry, I'm rushing through this a little bit. So this is just to show you that we don't just have pictures. We have a nice little formalization with somewhat like a semantics. This is mostly for Raquel. So there's something that could be type theory with records if you really wanted to, but there is a written notation for this. There is also an implementation of this, and that's probably more interesting. So since we've specified this model, we have an implementation ourselves of it, and other people have actually built one. Other people have actually built one as well, an implementation of this. So we have this as a foundation for building dialogue systems. And I just very briefly will show you one of the early dialogue systems we built with this. And this was joint work with Gabriel Skanse when he did a postdoc in my group a while ago. The system you're going to see, so our aim here was to model fast and fluent turn taking. What's going to happen here is the system is not leading very deep and meaningful, well, meaningful, yes, but not very deep conversations. What the system can actually do is the user dictates string of numbers to it, and the system will try to sort of write down the sequence of numbers. And this is meant to be an as fluid, as natural interaction as possible. It's kind of like dictating a credit card number or dictating a phone number, right? So the user dictates a string of digits to the system tries to ground its understanding as quickly as possible, and that's how the behavior is driven. It is really driven by this desire to ground as quickly as possible. The processing based on the IU model. Okay, so here's the example. Will it start automatically? No. So this is a telephony system, right? So the user only, they had a headset on. The user doesn't see this. This is a view of the brain of the system. What you're going to see is you're going to see digits appearing here. So this is sort of the belief state of the system, right? So the system will show here what it believes that the sequence of numbers is. And the certainty, the confidence of the system in its hypothesis will be encoded by saturation. So the darker the font is, the more certain the system is that this is the right understanding, right? And again, this is not what the user saw. This is what you have the privilege of seeing the brain of it. The user just spoke to the system, right? And I would like you to pay attention to what's happening here, and also to if you think that the interaction is fluid or not, especially if you have experiences with typical dialogue systems. Here's a hint, the answer is yes. I'm hoping that you find that. Okay.
253. Okay. 45. Sorry, do you mean 45? No, 45. Okay, 405. Yeah, and 684. Okay. 712 9. So, from the start, 253. Yeah. 405. 664. No, 684. Okay, 684. And then 7129. That's right.
Okay, so could you actually hear this? Is it possible to hear this? Okay, good. So yeah, I'm hoping you agree that this was more or less fluid. There were a couple of potential for misunderstanding. There was this 45. This could mean a 40 and then a 5, or it could mean a 4 and a 5. And the system noticed that there was potential for misunderstanding there and tried to clear it up. How did we do this? Well, first of all, we very cleverly chose the domain. I can say this because this was Gabriel's idea. There's very little predictability in these number sequences, right? There's very little syntactic structure to guide you on how one of those packages when it ends or not. So people naturally use prosody, use melody quite a lot to signal this. So we did a little corpus study before, and people really do something like 253, 789, 123, right? So people really do us a favor there and use a very clear prosody. So we had a classifier here, a machine learning classifier that tells us whether we think that this is a rising prosody or a falling prosody. And if it's a rising prosody, we provide by default these short feedback utterances. And if it's a falling one, we assume that the whole sequence is over, and various things. So we have plans for these grounding utterances, and these plans are cancelled if it actually continues. I'm not going to go into more details, except that to say that people liked this better than a non-incremental version that we compared it with. I want to talk about this briefly. So this is another, this was Okobus's PhD project, where we try to scale this up a little bit to more semantic content, but also the idea of having a longer information sequence being packaged into smaller installments is there. And it's this, surprisingly. I was very surprised to see this yesterday in Simon's talk. So yeah, we got undergrads to play this, not apes, and it didn't spontaneously occur. We actually made them play this, and it's a domain we've been working on for quite some time now. And these are pentominoes. These are not tentrominoes, whatever. These are 5 thingies, not 4. But anyway, so what the system is doing here is, and this time it's visual. It's a multimodal system. The user can actually see this, and the user is supposed to be. The user gives instructions, and the system is supposed to execute the instructions as soon as it can, but not earlier, right? And if you pay attention, it's sort of signaling some things by a change in the shape of the cursor, and some things it will just ask. It's in German, but I think it's subtitled. And again, if you want the microphone. And again, I mean, you can see the interaction here. Again, this will not win any prizes for dramatic intensity, but that's actually kind of the point, right? The point is that it manages to break this down into small segments.
Lösche das blaue Kreuz. Welches Teil? Oben rechts. Okay. Genau, jetzt nimm das gelbe. Ja. Und drehe es. Ja. Links rum. Okay. Jetzt spiegele die Treppe. Okay. Horizontal. Genau. Jetzt lösche das rote. Unten rechts. Genau.
Okay, so the point here was that what potentially could be very long utterances are very naturally segmented into smaller parts here, and the grounding is happening on much smaller units, much faster, with the idea being that potential problems are picked up much quicker and can be corrected much quicker, as if you have longer chunks of information that need to be repaired. Here we are really acting as soon as possible, and I don't know if you could see it well enough for this. It actually is almost a little bit spooky, because we quite often get a hypothesis from the ASR before the word is actually over, right? So the word yellow, for example, it's acting on it when the person has to set G, and it's because at this point these are the only alternatives. It's a very small search space, and it's immediately acting on this. So to me, actually, this appears a little bit spooky, but our subjects, that's the interesting part, our subject really picked up the ability to produce very small utterances and what you might call incomplete utterances, right? So it doesn't really, the utterance boundary isn't really that important here. It's more about information chunks. So yeah, people like that. Interestingly, it's not necessarily a higher success rate, but people judge this as more natural interactions. Okay, so that was the part on incremental processing, where we try to be faster with our decisions. Yes?
So I'm wondering to what extent this type of processing is actually kind of compositional in a certain way. So, I mean, you've shown very nicely that when there is one specific task context and you know one can be quite clear about a lot of kind of variables of the problem, then it works quite well and quite naturally. Mm-hmm. Could I take these blocks for different subtasks and so on and put them together? I mean, would it be relatively straightforward to introduce some meta-level control and have these kind of subunits? And has that been done, or are there other difficulties that you then get?
No, I think this is quite generally applicable. The way the information would be segmented is different, and again here this grounding criterion that I talked about earlier. So it kind of, how small you make the segments and how the dynamics plays out depends on how important it is to get the information across, right? And that's again why this numbers domain is quite useful, because there you really have to identify the signal. There's no way you can infer parts of it by understanding the other parts, right? You just really need to get every digit right. And that's why when we dictate phone numbers, we have this protocol as well, where we repeat it back immediately. You wouldn't normally read out the full phone number and then expect the person to read it back. You break this down. If you're doing small talk, on the other hand, it would be really weird if the other person interrupts you all the time and says, "Oh, Peter, oh, yesterday, oh, at the beach, oh, a drink, oh, okay, yes." I mean, you can do it, but it would be, there's no need for breaking it down. So there's a balance, and you want to reach a point where it's economical to do this. But I think the general principle transfers to all kinds of domains. Okay. More questions about this? So this is something that even commercial systems are moving towards. As I said, Siri, for example, is trying to give you replies more quickly these days as well, using some form of incremental processing inside as well. Okay, but now we move to the second part, where we actually want to assume that we're in a shared physical environment. And we started with the assumption that we can both the user and the system can perceive a third thing. So we are in a shared physical environment and we are perceiving our environment. And again, incremental statistical NLU. So we are keeping the requirement of incrementality. So this is sort of a given for us, but we are adding the situated, physically situated component. And it's a statistical approach, and this is Casey Kennington's PhD work. He's nearing the final year of his PhD. Okay, so what we have are situations like this. And now if we suppose that B says take the red cross, we want A to understand not only that B wants a red cross to be taken, but we want A to understand that it's this particular red cross that they're supposed to take, right? And of course we are replacing A here with a computer. Again, we're using our incremental units model, but we're extending this now with an information state, with hypotheses about the real world, hypotheses about the visual surroundings. There are these objects, and we update, when we have new percepts, we update this with a representation of the surroundings, and maybe something's happening in the real world as well. It's the same principles, basically. Now, what happens for an utterance like take the red cross? We build a semantic representation, a conventional meaning, a representation of the conventional meaning of this. But as we said before, certain elements need contextual input as well. And a definite article, the red cross, this suggests that it's something that is somehow contextually specified, which particular one it is. right? It's not an indefinite, it's a definite article. So what we want is we want this variable here to be identified with a particular object. And so we have a grounding, informational grounding here in the words that were said, but also in the actual object or in the mental representation of this object here. Okay? And we do this stochastically. So what we want is a distribution over intentions. Let's simplify this and we call this intention. We want a distribution over intentions. Which object here in our setting, we are always talking about these objects. Which object are they actually talking about? Or more specifically, given the speech signal and given the state of the world, what is the most likely intention of the speaker? When you have something like this, your first impulse may be to try base rule on it and to come up with a generative model of it, right? So very straightforward. We need a prior and the data likelihood, a likelihood function here. And how are we setting this up? Well, so if you squint your eyes a little bit, then you're already kind of seeing the graphical model in here. If this tells you anything, then that's good. If it doesn't, then the idea is this is a particular way of specifying the joint distribution over these variables here. And the particular way we're setting it up is, so the point is that we need to find a link between our observed things, the speech signal is observed, the current word maybe this is, and the state of the world is observed, and we want to know the intention here. The way we're representing this is a little bit different. Actually, it's like this here. So we assume that there is a latent variable R, and that's the thing that mediates the world and the utterances here. And this R here, these are the properties of the objects. These are the observable properties of the object. This marginalization malarkey here doesn't really need to interest you so much. Okay, so the story here is, it's a nice generative story again, is we are flipping this around the way you do it with when you have a generative model. We're flipping this around. We're interested in, so this is what we're observing, and we're interested in what's causing the observation, and we're kind of turning this around. We have the model where we say, okay, first I select my intention. First I select which object I want to talk about, and then the way this model works out here is then I, for each property that this object has, I check how salient this property, so this is this model here, I check how salient this property is for this given candidate object, and how likely this particular property is to have brought about the word I'm looking at the moment. Okay, and this is how the connection between world and words is made here. It will become clearer hopefully in a second. Okay, so what we did was we set up an experiment where it's a Wizard of Oz experiment. I don't know if you're familiar with this. So we had subjects come in and we told them they're talking to a computer, but in reality they were talking to a human because we didn't have the computer system yet. But this is made so that they bring with them the assumptions that they would normally have of talking to a computer. There was no visual contact between the agents, so they had a shared screen. They saw what was going on there, but they didn't see each other. And of course, so this was a computer display, and what's on the display is represented to the computer already in this symbolic form. I will come back to this in a second. So the objects here are specified really, the properties are written out here. So this here, object 1 has is star-shaped, has gray color, and it has a certain position, right? And this red cross has these properties. I can write this out as a matrix, obviously. So which object has which properties? It's a very simple encoding of this. And this is actually where, this is how we get this model here. This is where we get the model that gets us from candidate objects to talk about to the saliency of the properties. We just assume that each property for a given object, each property that it actually has the same probability of being mentioned in the utterance, right? It's a very straightforward model. So what was a one hot type encoding here, so we just normalize and we say, okay, if I want to talk about object 1, then with 0.5 probability I will somehow verbalize the property that it's star-shaped, and I will verbalize the property that it's gray. Note that we don't make any typing here. We don't type the properties into shapes and colors. They're all just meshed together. Okay. So how well does this work? So we tested this on these data here. So this was the tasks. This is the joint game board. And this is the intended goal state. So the task for the user was to give instructions to the system so that the game board ends up looking like this, or at least this part ends up looking like this. Some pieces are to be deleted, other pieces are to be moved. We basically just wanted them to talk about this. So we trained, so this model is basically read off the properties. This is read off the symbolic representation of the game board, and this model here is learned from data. Given a property, what are the likely words that are emitted, sort of an emission probability kind of thing. And you can guess, you can get this easily from annotated corpora by just looking at what people actually said in these situations. And then we tested it on a held out set data. And here are just the results on the object identification task. It's quite high. If you can see this, it's a 90 number. The take-home message at this point is just it works. But the baseline is already quite high since there's not a high number of objects here. But it works. So this is one approach to grounded semantics, and one approach to connect words with the world. Maybe I haven't set up the problem quite right enough, but it's actually, I mean, this is kind of mystery how words can reach out to the world and actually mean something in the world. And here's a very simple first step at getting at this. We are by no means the first to do this, but it kind of works. But I want to talk you through in the remaining time to sort of the next steps we took, because we're getting to somewhere which is actually interesting, I think. So these were just the first attempts. This has obvious limitations, the setup, and the first limitation we addressed is the fact that there's a black bar between the computer system and the user, and we made it so that the computer can also observe the speaker. So they're not just having a shared physical environment, but they can also observe the speaker. And here, again, I have to shout out to Spiros Kousidis, who's a postdoc in my group, and he did fantastic work on a software suite, which we're doing this multimodal processing, which I will show in a second. So what we have now is motion capture and eye tracking and all other kinds of fancy stuff in there. So we recorded a new setup. It's again a Wizard of Oz setup, but we told the person, so the setup here is, the task is, the person is to think of one of those things, so to develop an intention to make the system identify one of those pieces. So maybe they when they see this, they go and think like, okay, I kind of like that one. And then they say, okay, select the pink S-shaped thingy in the top left on the top. And we told them that they can gesture as well. We went through a very convoluted process of not quite showing them how to gesture, but suggesting to them that they can do it so that they will actually do it. But anyway, so some of them did. And what we did in this setup here was we used motion capture, so we know what they do with their limbs, and we recorded eye tracking here. And with our little software suite, we can synchronize these data streams, the motion capture coming from a Kinect here, and the eye tracking is coming from a camera-based. The sound's not important here. And the eye tracking is coming from a camera-based stereo camera pointed at their head. So the green dot is where they're gazing at, and this is showing the eye tracking, the motion capture. Obviously, the visualization here is just so we have nice videos to show at conferences. The visualization is not the important part. The important part is that this is now all data that is synchronized with the speech. So we know we have much more information about their actions, more than just the linguistic actions. Okay, so this is a pretty cool thing. It's open source. Why is it moving again? It's open source, so if you want to make this kind of experiments, we have done some of the hard work for you already. Okay, stop, shut up. So how do we get this information about gaze, eye gaze, and gestures into this? We could be representing it here in the IU model as alternatives, additional streams of information as well. For this project, we didn't quite do this. We did something else, which I think is kind of interesting, also sort of from a philosophical standpoint. What we do is we make these things into properties of objects. So this object at this point here, this object will have the property of being looked at. So we're kind of sidestepping considerations of intentions here. We make this into a property of the object. This is looked at, and now a little bit later, this is looked at, and now nothing is looked at, and now all these things are pointed at. Pointing is fairly imprecise, right? So the way we compute what is being pointed at is we compute a vector between the shoulder and the fingertip. So this is kind of going there, and between the eyes and the fingertip, and that gives you sort of a cone, a very rough cone. So you can get, I'm pointing kind of this direction, but you can't really point very pixel precise at things. Okay. And how does that work? This is on, that's different data, so the baseline is lower, and also it's on ASR output, so all in all it's lower a little bit. The point at this point is here that it really adds information. It's complementary information, or it's information that helps us to get over. Well, that lifts our performance a little bit if we have information about looking, where people are looking and where they are pointing, right? So that's nice. I mean, that's why people point. Gaze is a funny modality because you're not really, as a human, you're not really normally able to tell where people are gazing at with that precision. But we made ourselves available of this information here, and it helps. But what I'm really sort of working my way towards is that we lifted the next limitation as well, which is that we represented the scene like this. So the computer already had perfect knowledge about the world here, because this is actually how the world was generated, and the graphics was generated. And what we did this summer, so we had Livia, she's a master's student at York University. She came to visit us for a research internship over the summer. And what she did was she used very simple computer vision techniques on this. So instead of giving our system these representations, we gave the computer only the images, and based on edge detection. CV techniques like edge detection, there are little gray edges here, which you can't see, and other fairly standard stuff. Actually, what we get out now are distributions over these properties. So instead of having perfect knowledge about the world, we now have some uncertainty. At least that was the idea. If we plug in these images, it's too simple, actually. What we get out are not really distributions. They're very spiky. We basically get out this more or less. So what we did was we filtered these images. We systematically shifted the colors around, and we distorted the shapes to make this a little bit harder to get actual distributions out. How do we get this into the system here? Well, where before we knew with certainty that an object has the property of being star-shaped and it's not cross-shaped, now we have distributions over this. So we assume with a 0.8 confidence, we assume that it's star-shaped, but it may also be cross-shaped, right? So we have classifiers for shape and color and stuff. And again, it's very straightforward to get this into this model. You just renormalize, and there you go. Okay, so the results, and this now, it's all a bit of a mess, unfortunately, so don't really look at the numbers. This is now with the with the transcribed utterances and not with the ASR output. That's why the numbers are higher. What we get is, so if we use the symbolic representations as before, we get this performance. And if we use the filtered images with a lot of uncertainty about the state of the world, we get this performance. If we take the argmax, if we take the best one, but if we actually plug in the distributions, we fare better. So the take-home message here is that we preserve the uncertainty, and it's all very nice. And we have connected, so this is a better way, I believe, of connecting the language with the world. But one last bit. I don't know if this is the same in other fields. In natural language processing, it's kind of well known that generative models, well, they perform well if you have a lot of data. But the problem, of course, is that you need to model the whole joint distribution, even if you just care about the discriminating between classes. So typically, discriminative models perform much better. And that's what we tried next. A discriminative model that directly goes from the world to the candidate. And what we did specifically is, so this is the model here, specifically is we trained a little logistic regression or one-layer neural network, I guess, that takes as input a feature representation of the visual scene of one candidate. And here's kind of the trick a little bit. For each word, we trained a separate classifier, right? So we're treating the word now, the word is associated with a classifier. So in training time, what we do, for each occurrence of a word in the corpus, we pair the word with the features of the object that the utterance referred to. So we know in our corpus, we know which pieces the utterance is referred to. And each word in the utterance is paired with the visual features of the object it refers to. And these are positive examples. And it's also paired with a number of randomly chosen other objects in the scene. Okay? So let's say we have the word cross here, and we have an utterance, take the red cross. And the classifier for the word cross will get the feature representation of the red cross as a positive example, because we know that this is what was referred to, and it will maybe get the star as a negative example. This is a little bit dangerous because it might get another cross. There may have been another cross in the scene as well, a blue cross, right? So it will get the blue cross as a negative example, even though it's also a cross. But the idea here is that this happens sufficiently rarely to not endanger the performance overall. But if we have data that is completely ambiguous, completely ambiguous to this, then we will have a problem. So what I'm driving at here is this is a little bit like you can imagine, you can set up the situation where you have language learning in a child, right? So the child hears the word cross and it has some way of figuring out what the intention is of the other person. The other person is doing something with the cross, right? And they're saying the sound cross. And at first, the child does not make the connection. It has no way of making the connection between the sound cross and the actual cross. But it sees enough of those instances of this to be actually to train a classifier for the word cross, what it means, what typically happens when someone says cross. Okay, it performs better than the other model, so that's nice, but sort of the nice thing about this, the nice property is that we can plot it like this. So once we've trained these classifiers, here's the response of various classifiers for various words. So this is the classifier for the word blaue, blue in some declination, blue. And we're presenting objects where we artificially change the color, the representation of the color, right? So the color spectrum here. And if I step through the color spectrum, the response of this classifier is quite nicely to like blue-ish objects, right? So something seems to be happening here which suggests that, yeah, that something's happening that makes kind of sense. So this is the word blue, this is another form of the word blue, and it's peaking somewhere here. I'm not quite sure why it likes black so much. So this is the word red, two variants of the word red, and they are kind of peaking here in the spectrum, right? So we are giving a lot of examples to this, and it's picking up on the discriminative features that the word seems to be speaking about. And as a sort of sanity check, this is the classifier for the word das, the article, and it's flat across the color spectrum, right? Because das occurs in all contexts. So it occurs for all objects with various colors. And it's kind of nice. We didn't put this in, right? We didn't put in the fact that these are color words and these are articles that have nothing to do with words. So this was automatically learned. This automatically falls out of making lots of observations, right? And interesting interferences. Well, no, they're on the next slide. So these are articles here, and this is a shape. This is cross. And again, cross doesn't really denote a color, so it's flat. And here is the same idea, but played with different shapes. So we changed the shapes. And these pentomino shapes, they actually have, there's a sort of a standard encoding for them in terms of numbers, in terms of letters. But our subjects didn't know this, right? And I'm just using this here so I can label these graphs nicely. So what this is the classifier for the word cross. And it likes the cross, obviously. But it also likes this piece here and this piece. And you can kind of see where this is coming from, right? I mean, these are crosses. The descriptions may have been the cross with some pieces moved or something, right? But it's completely left cold by this piece. Well, interestingly, it also likes this piece, which is very much not a cross. Okay, so this here Winkel is angular piece. It likes this one most, but it also fires on this one a little bit. Again, you can kind of see post hoc, you can kind of make reason for this. And again, the sanity check here, this is the word symbol and sort of an equal response. This is the word form. This is the word square. So, and it picks out things, picks out this guy here, this guy with P, this guy, and this guy, and this one. Okay, but it's certainly, it's making a distinction. I think so these are colors here. Oh, that's unfortunately, unfortunately, I don't have one. You can't really see it much on here, but the articles actually, they do discriminate a little bit again among the shapes. Does anyone have an idea why this might be the case? So the articles, they are, this one doesn't so much, but eine does much more, and die does much more. I guess you need to know a little bit of German to have an idea on this. Right. So so German articles code gender as well, and for some reason these things have grammatical gender, so they're not quite compatible, right? And the classifiers pick up on this. I think this is still kind of a nice result. The idea is that this is sort of a little bit like a language learning situation, and unless you get much more evidence, then you would just make these connections. You need to learn more structure, as Simon told us yesterday. The second step then would be to induce structure on top of this. Okay, so we have a model here that learns from annotated data and learns sort of a connection, to make a connection between words and the world, or rather percepts of the world. It can be applied incrementally. I haven't really talked about this, but all this is done incrementally. So we form this hypothesis while the utterance is going on. We don't wait for the full utterance to process it. We do this looking around in the world incrementally. We can make use of additional information sources such as gestures and eye gaze, and it works with non-symbolic input with images, and it performs relatively well. So what we're doing at the moment is, it's not quite finished, unfortunately, yet. So what she actually did was not process images, but process videos. And so this experiment we have here, it's tracked, it's motion capture done with the Kinect. And that's actually why this is jumping around like this. It's quite noisy data, right? I love this. So she's very happy with herself. she's finished something here. So what we can do with this data is the idea is to do this more, well, we will call it unsupervised because that sounds nicer in paper titles. But the supervision signal is coming actually from observing what this person is doing, right? So we know what is being said, and we know which pieces are being manipulated by the person. So the idea is, and it's looking promising. The idea is that when we know that something has been, we notice that something has been touched, a piece has been manipulated. We look at the words that were said immediately before that, and we then learn that these words may have something to do with this piece. And we have lots of data like this, and the hope is that we are getting what you saw on the earlier slide. We're getting this is coming out of this. Well, without manual annotation effort. That's the point here, right? So the idea is to learn the meaning of words by observing people competently using them in the real world. Okay, I have more videos of this, but I will skip this. Can I skip this? I can skip this. Yes, because I'm nearing the, ooh, wow, I'm nearing the end here. Okay, so future work, there's an elephant in the room here, and the elephant is called compositionality, and like everybody who works with distributional semantics, this obviously is a form of distributional semantics, except that the contexts we use are sort of physical real-world contexts and not just corpora, but it is a kind of distributional semantics, and no one really knows how to do compositionality with this, right? So how would we learn what light blue means, what the light means? We can learn what light blue means, the n-gram light blue, that's easy. But how do we learn the contribution of the light when we have the classifier for blue? to the very right. So I didn't talk about this, but we've learned spatial terms as well to the left top. But how do you learn any kind of modifiers, any kind of structure on top of this? And yeah, we don't have a very good answer there. We have a hunch, but that has to be tested out. Some other things we're working on are sort of more descriptive gestures, things like we have a nice data set. I have a PhD student working on these kind of sort of root descriptions. There's something here, and then you go sort of like this, right? So we want to understand these gestures, and we want to understand them incrementally, live and online. That's some things we are working on. So the general tendency here is to be more in the world and perceive more the actions in the world. Okay. And with this, I guess are there questions on this part? You have a question?
Questions?
Could you explain again how did you train the neural networks?
Absolutely, yes. I skip over this a lot. So we have our corpus with utterances, and we know what these utterances refer to, right? So we have pairings of utterances and scenes. So we know what the world looked like when the utterance was made, and we know what the utterance was intended to refer to, right? Okay, and then we take each word of the utterance, and we pair it with the object, with the visual information of the object that was referred to. And the representation here, oh yeah, I completely glossed over this. So this is hue, saturation, and value, so representation of the color, the number of edges of the object, and horizontal skew and vertical skew. So very little information, visual information about these objects, right? So we have this vector. For each object we have a vector, and we pair. So the vector is the input, and the output for the classifier for this word is supposed to be 1 when you feed it the visual information of the object that the utterance referred to, and it's supposed to be 0. It's a negative example when you feed it the visual information of an object that was not referred to. Okay, so from each scene we have one positive example because there was one object that was referred to, and we take the other objects that were not referred to with this utterance. We take some of those, not all of those, I think 5 or something like this, 5 of those as negative examples. Okay? And as I said, this is a little bit dangerous because the negative examples may actually, for this given word, in reality, if you just look at the word, should have been positive examples as well. There may have been several crosses there. But yeah, the way it works out is that the chance is much higher than that they are really negative examples than that they are positive examples. Yeah, that's basically the training. So each word is a classifier.
All the pipeline that you showed, I mean the actual voice recognition and
yes,
so the corpus is
yes. So we are assuming that we know the word identity. So this is for a known word. Yeah, but this is not anymore. We're not classifying the shapes here. We're putting in sort of relatively raw features here. But yeah, I mean, if that's what you're getting at. What sort of looms in the background here is that you would want to do deep learning, and you would want at the bottom you would want to have the signal really. Ideally you would really want to have the speech there and the images, and just sort of throw this into your network and wait a couple of hours, and magic appears and everything works out. But we're not quite there yet. And that would still not get us further with the compositionality, yes, but that would give us more publications because we could put deep learning in the title. Deep learning, yes. But no, this is shallow learning here. Yeah, I mean, I've described it like this. You can set it up as a maximum entropy model and look at all the objects in the scene, but these are technical details, but this is how this is set up. And yeah, you're right. The uncertainty of the speech recognition isn't really represented here, but it's easy to bring this in as well. You have confidence levels for each words, and then you add this up and hope that something happens. Okay. Any more questions?
Okay, so
Hang on.
if there
I'm not quite done. I have.
you have more.
So yes, I have to shout out to the people paying for all this. So this is great. I actually started at the University of Potsdam with this. I'm now at Bielefeld University, so I don't seem to be very lucky in choice of places in terms of beauty of the buildings. But I found people who actually pay for this, and I found people who actually do this work that I can talk about. So yes, these are my collaborators. And now I'm done. Thank you.
Thank you very much.